One dome, 20 feet across, from 2 boards you already own. Before any mathematics, here is the finished thing, drawn to scale with a 6-foot person beside it. 20 feet across, 10 feet to the crown, about 300 square feet of floor. Everything in the next half hour is in service of that object. Where its 2 strut lengths come from, how to cut them, how to join them, how to stand them up, and how to know you got it right. Hub, strut, panel, chord factor, frequency. Learn them on the real thing. A hub is a joint. A strut is a straight member between 2 hubs. A panel is the triangle they enclose. A chord factor is a strut's length divided by the radius, which is what lets one drawing serve every size of dome. And frequency is how many times each edge of the parent shape was divided. 2, in this case, which is where 2V comes from. A triangle cannot change shape without changing a side length. Push the top corner of a square frame and it folds over into a diamond. No side got longer, the shape just moved. Do the same to a triangle and nothing happens because moving any corner would have to stretch a side. That is the entire structural argument for a geodesic dome, and it is why the frame carries load along its members rather than bending them. 20 equal triangles are the closest a regular solid gets to a sphere. Of the 5 regular solids, the icosahedron has the most faces and the most evenly spread corners, so it needs the least correction when you push it out to a sphere. That is the only reason it is chosen. It gives 20 equilateral launch pads and 12 corners, and every geodesic dome in common use starts here. The golden ratio places the parent vertices. It is not the strut ratio. The 12 corners of an icosahedron are 3 golden rectangles standing at right angles to each other. That is where the golden ratio genuinely lives in this shape. It is worth being precise about because the ratio of the 2 finished strut lengths is not phi, and expecting it to be has sent a lot of people down the wrong path. One division turns coordinates into numbers you can scale to any size. Divide every corner by its distance from the center, and the solid now sits on a sphere of radius exactly 1. From here on, every length we measure is a multiple of the radius. So the same drawing serves a garden dome and a hanger. This is the single most useful move in the whole derivation. 30 parent edges give 30 midpoints, and they're all too close in. Take the midpoint of every one of the 30 edges. That is just the average of the 2 ends, and it is easy. But those midpoints sit inside the sphere, not on it, because a straight line between 2 points on a curved surface always cuts the corner. Leave them there, and you have a faceted lump, not a dome. This one move is what creates the second strut length. Slide each midpoint straight out from the center until it reaches the sphere. Nothing else changes. But by moving those 30 points outward, every triangle around them changes shape, and the edges that used to be equal split into 2 different lengths. That is the whole origin of the 2 cut lengths in your shopping list. 120 edges collapse into exactly 2 numbers. Measure every edge on the finished sphere, and they fall into 2 groups and only 2. The shorter one runs from an original corner to a projected midpoint. The longer one runs between 2 projected midpoints, and it comes out to exactly 1 over phi, which is the one place the golden ratio does show up in the answer. Floor grows with the square of the radius. Volume grows with the cube. Now pick a size, and pick it for a reason. Doubling the radius gives 4 times the floor, 8 times the volume, and 4 times the skin you have to buy in waterproof. Headroom at the wall is the thing people underestimate. At the very edge of a hemisphere, there is none at all, which is what the riser wall later in this lesson is for. 26 hubs in courses at heights you can measure before you build. Cut the sphere in half, and the hubs sort themselves into level courses. 10 on the ground, then 2 rings of 5, then 5 more, then the single hub at the top. 26 joints in total. Those ring heights and diameters are your check numbers during the race. so write them on the drawing before you start. Two measured members imply two radii. Fit them, do not average them. You measured 72 inches and 63.5. Each of those implies a radius on its own, and they disagree slightly because real members contain cutting and measuring error. The right move is a least squares fit that weights both, not picking whichever one you trust more. That fit is the radius the rest of this lesson uses. The connector decides the deduction, and the deduction decides every cut. A steel star plate, a beveled timber joint, and a drilled hub ball all build the same geometry, but they eat different amounts of strut. Choose the system now, build one joint for rail, and measure how much shorter the members have to be. Everything downstream depends on that one measurement, and no catalog number is a substitute for it. The geometry gives hub centers. The saw needs something shorter. Every number in the derivation is hub center to hub center, because that is what the sphere is made of. The stick you cut has to be shorter by whatever the two connectors occupy. Note that the deduction is the total across both ends, not per end. Having it by mistake is one of the most common ways a dome ends up refusing to close. One line of arithmetic gives you the angle the strut leaves the surface at. A strut is a chord across the sphere, so it dips below the surface between its ends. The angle it makes with the surface at each end is exactly half the central angle that chord subtends, and the central angle comes straight out of the chord factor. That is the angle to tip a hub plate to, or to cut a timber end back to, and there is one value per strut class. Two panels fold along every interior strut, and there are only two fold angles. Where two panels meet along a strut, they are not in the same plane. They fold. If you're skinning with rigid sheets, the edge of each panel wants to be plane to half that fold, so the two faces meet cleanly. There are exactly two fold angles in the whole dome, one along each strut class, which means two saw settings and no thinking at the bench. 5 hub types, and they are not interchangeable. Grouping the hubs by how many struts arrive and at what angles give a small number of distinct types. Make a set for each type, keep them in separate label boxes, and check one against a drawing before you make the rest. The base hubs are the ones to make first, because they also have to take the anchor bolts. Choose the stock length before the radius and the offcut nearly vanishes. Here is a real cost that geometry lessons never mention. At this radius, a standard 8-foot stick yields exactly one strut and throws the rest away. A 16-foot stick yields several. The right time to notice that is while the radius is still adjustable, because a small change in radius can move you from one piece per stick to two. Cut every piece of one class before you move anything. Set a stop block for the first class and cut all of them without touching the setting. Keep the very first good piece as a master gauge and compare the rest to it rather than remeasuring with a tape, because a tape introduces a new error every time you use it. Label each piece as it comes off the saw. Then, and only then, move the stop. 65 members, 2 lengths, and a count you can hand to a shop. This is the whole order. 30 of the shorter class and 35 of the longer at the cut lengths we derived, plus the hub schedule. At spares, 2 or 3 of each class costs very little and saves an entire afternoon the first time a piece splits or a cut goes wrong. 2 triangle families repeat all 40 times. Jig them on the ground. The dome contains only 2 kinds of triangle, 30 with 2 short sides and 1 long, and 10 with 3 long sides. Lay one of each out on a flat floor, screw down blocks to make a jig, and assemble the rest inside the jig. Every panel then comes out identical, and the raise turns into bolting known good pieces together rather than fitting each one. A 10-sided ring, set out from the center, checked on the diagonals. Drive a pin at the center and swing the base radius to mark all 10 hub positions. Do not step around the ring measuring side to side, because every small error then adds to the next one. When the 10 are pegged, Measure the long diagonals. On a regular 10-sided ring, they're all identical, so any difference is telling you exactly where the setting out drifted. Piers, a ring beam, or a slab. Whichever you choose has to be level. A dome puts a concentrated outward and down load at each base hub, so the foundation either has to catch each one individually with a pier or tie them all together with a ring beam or slab that resists the spread. The structural choice is yours and your engineers. The one non-negotiable is that the 10 bearing points end up on one level plane. The cheapest usable space a dome will ever sell you. A hemisphere has no headroom at its edge, which makes the outer ring of floor nearly useless. Stand the whole dome on a short vertical wall, and every point of the shell rises by that amount. So the perimeter becomes furniture height or door height. It costs one ring of studs, and it changes the plan completely. Decide on it before you set out, because it changes the foundation. Never build up one side. The shell is not stable until a ring closes. Bolt the base hubs down, then work upward in complete courses. A half-built ring is a row of unstable triangles, and it will lean. A closed ring is a rigid hoop that holds its own shape. Prop each course until the one above it closes. Measure the diameter across each finished ring in 3 directions before you begin the next, and correct there rather than higher up. If the last hub will not fit, the error is in the ring below it. The top hub is where every accumulated millimeter finally arrives, so it is the honest test of everything below. If the 5 struts will not reach it cleanly, resist the urge to force them. Go back down and measure the ring beneath. Nearly always it is slightly out of round or slightly out of level, and correcting it there is far quicker than fighting the crown. A 10-sided ring amplifies a strut error by exactly the golden ratio. Here is a number worth carrying around. If every base strut is 1/8 of an inch long, the base radius is out by 5 times that, and the diameter by twice again. The same golden ratio that placed the parent corners now governs how your mistakes grow. It is not a large factor, but it is a multiplier, and it explains why domes drift bigger rather than smaller. Member, triangle, ring, radius, height. In that order, every time. Check a member against the master gauge. Check a triangle on all 3 corners. Check a ring on its diameter 3 ways. Check the radius from the center pin to each hub. Check the apex height against the radius, because on a true hemisphere they're the same number. Each check catches what the previous one could hide, and doing them in order is what stops a small error becoming a structural one. 40 panels, laid so every lap sheds downhill, sealed at every hub. Start at the base and work up so each panel laps over the one below it, exactly like roof shingles. Every hub is a junction of several panel corners, and those are the leak points, so flash or tape each one before the next course covers it. Give the base a real drip edge that throws water clear the wall. A dome almost never fails structurally. It fails at its seams. Take whole panels. Cutting a strut means replacing a load path. The clean way to make an opening is to leave a panel out and frame the triangle. The frame is untouched, and the shell keeps working. If you must make a bigger opening, head it with a member at least as strong as the ones you removed and get that detail checked, because a dome carries load through its net and a missing strut is a missing path, not just a missing stick. None of them are geometry. All of them are avoidable. Domes rarely fail because the arithmetic was wrong. They fail because the connector deduction was guessed instead of measured, because the base was not level, because someone built up one side instead of in rings, or because 2 similar-looking members got mixed up. Each of those is a habit, not a calculation, and each is cheap to fix before you start and expensive after. From the golden ratio to a building you can stand inside. 5 places 12 corners. Normalizing puts them on a unit sphere. Having every edge and pushing the midpoints out gives 2 chord factors. One radius turns those into two cut lengths. A connector deduction turns those into saw settings. Jigs turn saw settings into identical triangles. Rings turn triangles into a shell, and a skin turns a shell into a room. Every number came from the geometry, and every one of them can be recomputed instead of trusted.